Let's tackle one more stack problem before calling it a day. And this time, we want to find the minimum element in a stack in constant time. Now, it's important to remember that it's always easy to iterate over all the elements of a stack and find the minimum when asked for. But that takes order of n time. What we need to find is the minimum element no matter what operations we perform on the stack, and that too in constant time. Let's see how we can do this. Space is not a constraint. Let's move on to another stack based problem. And in this one, we want to find the minimum element stored in a stack in constant time. Typically, as you are adding elements to a stack, and let's assume for simplicity that all of them are integers, the way you track the minimum element is you'd basically look through the entire stack whenever get minimum was called and return the minimum element that you encountered. This is order of n. For every get minimum call, you'd have to basically iterate through all the elements in the stack. We want to improve on this and get the minimum in constant time. Note that as we push and pop and perform a whole bunch of operations on the stack, we always want to know what the minimum is and we want to know it in constant time. Now, this is different from just having a single variable storing the minimum value. It's because each time you pop, if you popped the minimum element, you'd have to basically look through the entire stack again to find the new minimum. This is what we want to avoid as well. Let's see how we can do this. What we'll do is we'll keep track of the minimum element for each element we push onto the stack. Basically, each time you do a push onto the stack, we'll say at this point in time, of all elements which exist in the stack at this point in time, including the one we just pushed on, this is the minimum. We'll have two stacks, one to hold the actual elements and another to hold the minimum element corresponding to every element that we've added to the original stack. We have two stacks running at a point in time. One which is purely to store the minimum element for every corresponding element that we've added to the original stack. So, how would we maintain this dual stacks? When we add an element or push an element onto the stack, we compare it with the last minimum element that we saw. That is, we compare it to the top of the second stack, which holds the minimum elements. If the new element that we're adding is a new minimum, we basically add this new element to the minimum stack as well as the original stack. If the minimum remains unchanged, then we simply re-add the old minimum to the minimum stack and add this new element to the original stack. And we do exactly the same thing while popping an element from stack. We pop both from the original stack as well as the stack which holds the minimum element. Let's visualize this because it's hard to kind of just talk about it in words. We have two stacks, the original stack and a min stack to keep track of the minimum elements. The original stack is where we'll store the elements as they come in. That's the stack we push the elements to. Let's say we're adding 4 to the original stack. Since the min stack does not contain any elements, 4 is the minimum at that point in time. So we add 4 to the min stack. Now, let's say we want to add 5 to the original stack. We'll compare this value 5 to the value on the top of min stack, which is 4. The minimum in this stack is still 4, so we re-add 4 to the min stack. So for the two elements we have on stack right now, the minimum is 4. Let's move on. Say we add 3 to the original stack. This 3 is actually a new minimum when we compare it to the top element in min stack. This means that the min stack value should now be 3. So what we'll do is go ahead and add 3 to the min stack. So for the 3 elements that are in the stack, 3 is the minimum. If we add 2, then we add 2 to the min stack, just like before. Now let's say we added 9 to the original stack. This does not affect our minimum. It is still 2. See that we have a minimum value for every element in the original stack. Whatever operations we perform, if we perform it to both stacks, we'll always know what the minimum is. We've kept track of the minimum at every step. Let's pop elements from the stack. We want to pop 9, which means we also pop the top of the min stack, that is 2. The new minimum for the elements on the stack is still 2. If we pop 2 from both stacks, the new minimum will be 3. If we pop 3, the new minimum will be 4. Note that we always keep track of the minimum in the min stack. Now that we've seen how this problem can be solved, let's take a look at the code as you can see on screen. We've implemented a class called minimum stack. It holds 2 stacks. One is the original information, that is just stack itself, and another stack to hold the minimum element at any point in time. So we have a stack within it and a minimum stack. Now, for every push operation, we basically peek into the minimum stack and see whether the element that's present in the minimum stack is smaller than or larger than the element we are seeking to push. If it is smaller, then we simply push that into the stack itself. If the new data that we are adding is smaller, that is the element that we push onto the stack. Notice that we do 2 pushes, one on each stack. We push the original element onto the stack and we push the min that we have calculated onto the minimum stack. So the min could be either the data that is passed in for push, or it could be the minimum which already existed on the minimum stack. The pop method pops elements from both stacks. So at any point in time, minimum stack and stack should have equal number of elements. That is crucial. That's how it tracks the minimum at every step. And now for the all important get minimum, we simply peek into the minimum stack. It is an order of 1 operation. So we've achieved implementing minimum as an order of 1 operation.